All right, welcome to Morals Math Corner. Today we are talking about volume of pyramids and cones. Now I know that there have been a lot of formulas that we've been dealing with, but it's not really that much when you really think about it. And in this section, you're going to see a double use of the same formula. When we're looking for the volume of a pyramid or a cone, okay, we are talking about volume equals 1/3 the base area times height. It is almost like regular volume of any prism, which is base area times height. But this is 1/3 the base area times the height. And of course, again, here I have a pyramid for you where it identifies the slant height, okay, the apex or the vertex, the face in blue, okay, the height of the complete figure, which goes from apex all the way down to the center, just to give you again another glimpse of how to label a pyramid. Now that same exact formula is what you're going to use for also a cone. Cone, same exact formula. Volume of a cone is 1/3 base area times height. And again, I gave you another example of a cone where it shows you the slant height, okay, which is this guy right here, the radius, okay, it's not really highlighted down there, but the radius, and then you have the complete height from the apex or vertex all the way down to the base. Yes? Okay. So hopefully that makes sense. And it's very simple to use, very easy formulas. Now, we got to complicate it a little bit as always. Remember that we were talking about the frustum? Okay, well, we're going to talk about that a lot more clearly here. What I'm going to teach you now is applicable to both pyramids and cones. Okay, sorry about that. So, what we're going to learn now is applicable to both cones and pyramids. And it's basically a cross section. What's happening here is you have a smaller pyramid embedded inside of a larger pyramid. And let's first go over the labels of all of this, and then I'll show you how to work it, because it's really not that bad. This little red square right here, this guy, this is what's called the cross section, okay? And it is recognized by this symbol right here. When we find this symbol, we're talking about the area of the cross section, which again is this little red section right here. Okay? The B, we know the B already. The B is the base area. This guy down here. That's the base area. Now, the height from the vertex all the way to my cross section is called my K. It's in blue here. It's the height from the vertex to the cross section. And of course, the height from vertex all the way down to the base is my height. Now, that's all fine and dandy and very nice and sweet, but what does it mean? Well, you can find out a lot of stuff about this. What happens here is, it's a law, it's a theorem. The ratio of the areas of the cross section to the base area is equal to the height from the vertex to the cross section over the total height of the figure. And that's what I have right here. The ratio of the cross-sectional area to the base area equals the square of the ratio of the height from the vertex to the cross section over the complete total height of the figure. Okay? Yes, sir. The question was, is there any specific reason why you square it? Yes, there is. We can get into the proof. I'm going to be rude, though. I'm not going to prove it. We're just going to go ahead and say that's just because. But there is a reason, son. But we're not going to get to the proof. If you want to come early in the morning, we can do the proof. Yes, sir. The green area is not called the cross section. I made an error here. I apologize, and I thank you, son. That is the area of the base. Thank you. Okay. Awesome. Thank you, son. Does that make sense, guys? You sure? Okay. Let's do some examples now. Okay? Let's do some examples now. Okay. We'll start easy and then we'll get a little bit more difficult as the time progresses. Okay, let's first do number 1. For problem number 1 here, okay, it says here that the height of a pyramid is 21 and the pyramid's base is an equilateral triangle with sides measuring 8. What is the pyramid's volume? Now, bear with me here, okay? My drawings aren't so great, but we've got a pyramid with a triangular base. It says the pyramid's base is an equilateral triangle. So we know all the sides are going to be equal. And we have a pyramid. So I'm going to do the best I can here, guys. That's a horrible, horrible, horrible pyramid, but we're going to go ahead and say that looks great. Okay, so it says here that the triangle sides are 8. So the triangle sides are 8, okay? And remember, guys, let me make it a little bit easier. This is the triangle, and then these shoot up to a common vertex. Horrible, horrible pyramid. Horrible pyramid. Horrible pyramid, but it'll make do. So the height of the pyramid itself, I'm not even going to label the height. I just know that the height is 21, okay? And I have the sides of the equilateral triangle are 8. So remember that the volume is equal to the base area times the height. Well, does anyone remember, how do we find very nicely, quickly, and efficiently the area to an equilateral triangle? Yes, sir. Side squared over radical, side squared times radical 3 over 4. Very good. So it's going to be 16 square root of 3 times 21. Nice and easy. Divided by 3. So this is going to be 112 square root of 3 units cubed, because it's volume. Does that make sense? Yes? Okay. May I continue? Awesome. Let's do problem 2. Problem 2, they give us a cone. Cones are a little bit easier for me to draw. Still not perfect, but a lot better. This is H6. They give us a slant height of 10. And they want us to find the volume of this cone. Well, volume of a cone is 1/3 base area times height. So you got 1/3. What's the base area here? Pi r squared, so that's 36 pi. Now, the height. Whoever puts in the slant height here is wrong. Okay, slant height would be used for surface area, not volume. Here we're looking for the actual height, which is going to be 8 because this is a 3, 4, 5 triangle times 2, so that's times 8. So that's going to be in total 12 pi times 8, so 96 pi units cubed. Does that make sense, everybody? Yes? Okay, now I'm going to show you the cross-section example. It's not bad, it's not bad. Let me know when you're ready. No, I still see someone writing. You good? Thank you, son. Okay. So for problem 3. Okay. Bear with my drawing here as well, please. In the book, it's a much, much better drawing. But I think I have a decent chance of doing this one okay. Actually, that one came out pretty decent. They tell me that the height is 12 centimeters. And they tell me that the base area is 24 centimeters squared. We have two things to find here. A, I want the volume of the cross-section. Okay? Remember, the cross-section is that upper part. And then B, I want to find the, not the total volume, but the volume of the frustum. If you remember, the frustum in this case is going to be this part of it. The frustum is the part left over after you've eliminated the cross section. Okay? So I want the volumes here. Now, in this particular case, if you think about logic here, wouldn't the volume of the frustum just be the total volume minus the cross-sectional volume? So let's first find the cross-sectional volume. The cross-sectional volume is going to be, of course, 1/3 times base area times height. So I've got 1/3 times, okay, what is the base area here of this of this figure here? Okay, let's think about where we're getting stuck here, guys. Okay, they did not give it to you. The base area, yeah, that's for this, for the big whole entire volume. But I'm first looking for the volume of the cross section. So the B here is really the cross sectional area times the height of that actual cross section. Okay, of that actual cross section. Now, it tells you here that the cross section is cut 3 centimeters from the base. So if it's cut 3 centimeters from the base, what is my K? 9. The whole thing is 12, guys. And it's cut from 3 centimeters from the base. And 12 minus 3 is 9 centimeters, okay? You guys with me so far? The whole height is 12. The height of the cross section is 9. Absolutely, right? Now, I don't know how to do this. I cannot find this, but I do know that the cross-sectional area over the base area is equal to the K over the H squared. So the cross-sectional area, after you make that calculation, is going to be 27 over 2. Now that I have my cross-sectional area is 27 over 2, The volume of my cross section is 1/3 times 27 over 2 times the height of 9 because I'm dealing with the cross section. So this is going to go to 9. So that's 81 over 2, so 40.5. So 40.5 cubic, which is this, centimeters? Yeah. That's just part A. Does everyone see that? Now, part B, I want the volume of the frustum. Well, first let's find the volume of the whole entire thing. What is the volume of the whole entire thing? 1/3 times base area times a height of 12 goes to 8. So that's 96 centimeters cubed. So then what will the volume of the frustum be? Volume of the frustum is going to be the whole minus the small. So 55.5 cubic centimeters. Does that make sense? Yes? Okay. Awesome. Give me 1 second. Okay. I know it's been a long day, but we're going to continue. We're learning volume of spheres. Now, the volume of a sphere is very, very simple. The volume of a sphere is literally 4/3 pi r cubed. I went ahead and took out 2 images of spheres. Remember yesterday that I told you guys that it was made up of 4 circles, and I kind of didn't do that good of a job in drawing it? Well, hopefully this guy right here will articulate for you a little bit better what I mean. Okay? You have the main circle, then you have this circle, then you have this circle, then you have this circle.
So that's why you multiply the radius.
And that, no, you multiply it by 4. What do you mean? The surface area, no, but the surface area is 4 pi r squared. That's why we do it by 4, because there's 4 circles.
Yeah.
Okay? Now this is just r to the cube, 4/3 pi r cubed. Again, I'm not going to go through the proof. Just accept, I promise you that is the formula. I promise you, okay? And that's literally it. So I could give you an example like this. Find volume of a sphere with a radius of 6. Well, in this particular case, I know it's really hard, but it's going to be 4/3 pi r cubed. So this is 4/3 times pi, and that's going to be 36 at 216, correct? Yeah, right? 216. And then that's 3/6, so that's divided, so that's 72. 72 times 4, 288. 288 pi units cubed. Now, what if I said to you, find the hemisphere? Hemisphere is half of a sphere. Kind of like a semicircle, but they don't call it semisphere. They call it hemisphere. So this would be half. So 288 pi divided by 2 would be 144 pi units cubed. Yes? Hemisphere is just half a sphere. If I say find the surface area of the hemisphere, find the surface area, then divide it by 2, my man. But actually, that's actually a good question. Let me show you a little bit of a different. I'm very proud of you for asking that. Let's say I tell you to find find the surface area and volume of a hemisphere with radius, whatever, 4 centimeters. Please pay attention to this, because this gets people all the time. Pay attention to my logic, please, please. Okay, first of all, let's first find the surface area. Now, we know that the surface area of the whole entire sphere would be 4 times pi r squared. So that'd be 64 pi, correct, my brothers? Now, please pay attention to this. When I cut this in half, I basically have a bowl, right? Would dividing this by 2 give me the true surface area? No, it would not. It would give me the surface area of the outside. But would it give me the surface area of this circle? So when you're finding the surface area of a hemisphere, find the total surface area, divide it by 2, but then please remember to add the area of the circle itself, my brothers, which would be 16 pi, and then in total this would be 48 pi units squared. Please be cognizant of what I did there. I had a surface area, so it had the area of everything around that sphere. But when I cut that sucker in half, I was just left with the surface area, not the area of this capper. Does that make sense? So I had to add that area back into it. Does that make sense? Now, for volume, it's completely different. I'll get right back to you. For volume, we don't have to worry about that because volume is already calculating what's inside of it. So when I get the volume to this bad boy, it's 1/3 of base area times height. So I got 1/3 of base area here, I said was 16 pi. Yeah, I'm stupid. I apologize. Sorry out there in computer land. I just did a total brain fart. Volume here is 4/3 pi r cubed. Maybe I should learn how to read. So I got 4/3 times pi times r cubed, which is 64. And that's going to be 256, right? 256 pi over 3. Now, that's the whole volume. Now, to find the hemisphere, can I just simply divide this by 2? Heck yeah. So it'd be 256 pi over 6 units cubed. That would be the hemisphere. Now, why don't you add back the top part of the circle for the surface area, for the volume? Because it's already inside. You already have the total inside. It's like you filled up a balloon with water. You already filled up the whole thing with water, right? Let's say that whole balloon, the whole volume was 100 cubic centimeters. If I could magically put a super thin, flat piece of metal right in the center of it, and without having any of the water splash out, wouldn't I literally be taking half of the volume away there? So I don't need to add back this area. That is just for surface area. That makes sense? You sure? Awesome. All right, y'all. Well, thank you very much, and stay classy.